Hello everyone and welcome to another video. Today we are going to talk about the F equals MA 2016 number 23. In addition to solving this problem, we'll go over how to use small lengths and angles to try solving bigger problems that have very difficult shapes. So with that out of the way, let's get started. Okay, so this is the problem, and I'm going to post the problem on the screen right now. So try the problem when you have before I start explaining it. Okay, so now that you probably read the problem, let's quickly analyze what's going on. So we have some rubber band, some circular rubber band with radius r, mass m, and spring constant k, and then we're basically rotating this with angular velocity omega and the new radius of r prime. And we're trying to find this new radius. Okay, so let's think about how should we approach this problem. So the first thing that comes to my mind is to analyze a small section of the rubber band. So suppose that we have this rubber band right here and we right here and we're opening up to see this. So let's say that there's a small piece right here. So let's look at the forces that are on this piece of rubber band. So there's obviously going to be the two tension forces or the spring forces that are pointing downwards like this. Then that's pretty much it. And we also know that it's rotating. So the um, the downward force should be equal to the omega squared r, m omega squared r, because it's rotating. So that's our centripetal force. So let's say that this force is T. Okay, we can find T later, but let's just say it's T. And suppose this is the center. So we draw lines here and we draw it up there. And then we can label this as a very small angle. Because this length is super small, we can label this angle as like some super small thing. So let's label it delta theta. So this length goes around an angle of delta theta. Okay, so now we can try finding the angle or like the total force, centripetal force used in terms of t. So we know that these t are going to be tangent to the circle. So if we extend this, we get that this is just 90 degrees, and therefore this angle right here is going to be delta theta over 2. And the reason this is delta theta over 2 is because suppose this is the vertical. This line right here in the middle, that's the vertical. It splits this delta theta in half, so each of the halves are delta theta over 2. And if we extend this line all the way like that, then we can just basically move this upwards like this, such that the vertical is here, and we have this angle as delta theta over 2. And we know that this angle is 90 degrees, and we know that if this is the horizontal, this angle between the horizontal and the vertical is 90 degrees as well. So that means that the angle at which this tension force is from the horizontal is going to be delta theta over 2. And same thing on the other side. So for both sides, the angle from where it's from the horizontal is delta theta over 2. Okay, so now we have this angle, and we know that the centripetal force is going to be the force that's pointing this way, downwards. And this happens when we take the sine of this angle. So if we take the sine of this angle and multiply this by t, we get the centripetal force from one of the t's, but there's two of them. So you have to multiply this by 2. Okay, so now what do we do? Well, we can set this equal to our m omega squared r, because this is our centripetal acceleration. And this is going to be r prime because this is our new circle. But we can actually simplify this further, because since delta theta over 2 is such a small angle, we can use the following approximation, that sine x equals x. And this approximation is very useful when dealing with small angles so that your calculations become easier. So in this case, x is delta theta over 2. We can get rid of this sign and we can replace this with just delta theta over 2. And luckily for us, we can get rid of the fraction as well because we have a 2 times. So this is just going to be equal to t times delta theta times is equal to the mass times omega squared r prime, where r prime is the new radius. Okay, so now we see we still have a delta theta and we want to get rid of it, but we don't know how. So let's just continue solving and then see if we can somehow get rid of this delta theta. So let's try finding t, because we know that t is not one of the variables. We have k, which is our spring constant. So this kind of acts like a spring, and this is its rest length, which means that, so 2 pi r is its rest length, and then we can use the formula that t or f or whatever is equal to k times delta x, change in x. And in this case, the x that's changing is going to be 2 pi times r prime minus 2 pi times r, because the circumference is changing by that much. So then this is our delta x, and we multiply this by k. So this gives us our tension. So we can factor out the 2 pi, so then we get 2 pi k times r prime minus r times delta theta. So this is our fully simplified left side. Okay, how about the right side? Well, m is the mass of this small length right here that subtends an arc of delta theta. So we can rewrite m as, so we know that the total mass is m, capital M. We know that this m is going to be in a ratio of, so lowercase m to the big case M is going to be equal to this delta theta. Oh, that's a bad delta. This delta theta over 2 pi. Because m subtends the whole entire circle, which is 2 pi, and the smaller m subtends a small section, which is delta theta. So this means that lowercase m is just going to be equal to delta theta times m over 2 pi. And now we can plug this m back into this m in our centripetal force equation. So this is going to be equal to delta theta m over 2 pi times omega squared r prime. Okay, so now we can just solve for r prime. So let me just quickly erase some of this. Okay, so now we have this equation and we can solve. So let's expand the left side. So then we get 2 pi k times r prime minus 2 pi k times r. And we see that we have 2 delta thetas, so these delta thetas can cancel out. So that's very good. But now we're left with variables that we already have, and we have r prime. And so yeah, that's very good. So now we have, this is equal to big capital M over 2 pi omega squared r prime. Okay, so now we can move this term to this side and the other term to the other side. And this then gives us 4 pi squared k r prime minus m omega squared r prime is equal to 4 pi squared kr. And finally, we can divide both sides. If we factor out the r prime, we can divide both sides by 4 pi squared k minus m omega squared. So this ends up with, gives us that r prime is equal to 4 pi squared k all over 4 pi squared k minus m omega squared. And we're done. Okay, so this was a very interesting problem because these problems sometimes appear in the F equals MA, and they require you to look at a small section of the total object to see if we can try figuring out some relationships between the object and its forces. And in this case, we were able to figure out the net force on a certain object and set that equal to the centripetal acceleration, and then we could easily solve. In other cases, you may have to analyze the whole surface. And in other cases, you might have like a square or something like that. So a common strategy whenever you're approaching some of these types of problems is to just look at a small section and look at the forces on that small section. So yeah, thank you guys for watching, and I'll see you guys in the next video.